Hi, and welcome to another exciting edition of game shading techniques and training theory. My name is Nate Nestler, and this is for Hyperactive Studios. Okay, so real quick here, let's do a quick breakdown of this. This will all make sense. So say you have an image like this, a texture, for instance. This is a texture. And you were to get a sample of it, and say you're looking at a single pixel, and you have the surrounding pixels around it. And this would be what's considered a 3x3. And this is your center pixel that you're looking at. You could sample the surrounding pixels around it and do what's called a filtering technique. And this will allow you to blur these other pixels and all kinds of fun stuff with it. And you can also use this for edge detection. You can use it for oh gosh, so many things. You can use it for bloom, you can use it for glow, you can use it for blurring, you can use it for shadow blurs techniques, for blending things. You can use it for basically animated cartoon-like looking drawings techniques. You can do so many things. I'm not even going to bother going over it. All the stuff you can do with this filtering techniques, tons of stuff. It's really important. It's used for a whole lot of stuff, and we definitely need to talk about it. Okay, so say we were to access this. Let's look at how we can actually go about accessing these different pixels so that we can do one of these techniques. So I'm going to go ahead and pull this up here, and I've colorized these pixels. So the way these work here is you have different weights you can have applied to each pixel on here, and the centermost pixel is going to have the most weight. And so typically, almost always, you can do different shapes though with this weighting. So this is cool. Once you have these weights set up like this, you can just manipulate them to do, say you want to do a cross filter, or you just want to do a circular filter where you have the centermost points the strongest. Same thing in the cross too. Centermost points the strongest, and then your outer ones here are evenly weak all the way around. Whereas a cross one would be, these would be stronger, and these would be the weakest points here, and then these 4 points would be the next most strongest, and then this would be the strongest point of all for weighting. And in this way you can say that this point doesn't matter as much as this point here for blending the colors, for your averaging. And that's great because then that prevents you from blurring this one out too much and not having as much influence as it should and lose too much detail. So this is great because it prevents you from losing too much detail with these weights. As you can see though, it's in a basic grid layout here. So 0, 0 is going to be your first pixel here in the corner, and 2, 2 is going to be down here at the bottom. Whereas 1, 1 is going to be the center point, and it's typically going to be your highest weight. It's at the center of weight 11. So that's basically how it works as far as that goes, for how you would access these pixels around your surrounding pixel that you're trying to modify and create blur. Realize that we're computing this in a GPU. So we're doing massively multi-threaded computations. So this means every time we're sampling one of these pixels, we're doing how many computations, guys? 9 computations. That's right, 9 pixels here. So yeah, every time we grab one of these pixels, we have to grab the surrounding pixels around it so that they can be weighted and averaged, and so we can get our final blur point here, or glow point, or whatever, in the center, where we decide we're going to do with our filtering, for that matter. All right. And then you have your weights over here on the other side, on the left, here showing you how those can be weighed out, and basically which ones you would access for that. So let's look at some code, and let's not forget that this is a highly parallel problem, so we don't have to worry about if condition statement branching or anything like that. Instead, this is all computations that can easily be broken off into their own little parts in the kernel of the GPU for being processed with the memory, and it can be computed very quickly, very fast, and high speeds, and they can all be computed independently of each other. And that's a very important key point here with massively multi-threaded computations. They need to be independent calculations where they can be computed independently of each other. They don't rely on each other to be computed, and thus allowing it to be computed much faster. So each one of these is going to get computed 9 times per pixel, so it's quite a bit of image access. This would be very slow on the CPU. This is why we want to do it on the GPU, because it makes it run so much faster. It is way, way faster. This right now is what's called a box method, though, for filtering. There are other types of methods, like Lanczos, Gaussian. There's also Mitchell. Those 3 are my favorites by far. Lanczos and Mitchell are my 2 favorites of all, but Gauss gives you a nice blur if you're trying to get a blur effect out of it. So there's different types of filtering techniques, And you know, the box one's the fastest one. We are doing a 3x3, so it's way better than a 1x1. 1x1 would just be the pixel. This is a 3x3 because it's 3 pixels over and 3 pixels down. You know, so this is a 3x3. As you can see, 3 this way, 3 that way. So it gives you a total of 9 pixels when you do a 3x3. Some will see 4x4s, 5x5s, and 6x6s. It's about as big as I've seen is a 6x6. But realize you can do that. Okay, so with that said, let's look at our filtering here, code for the techniques. All right, so this is like a pseudocode, and this is just, let me go ahead and just break this down like this so we can explain it and how it works. Okay, cool. So if I have my pixel and my UVs, I subtract a step vertical, and you're going, well, that was going to move it down, right? Yeah, I was kind of thinking that way, but no. Think about it for a second. Your 0, 0 is up here, right? And 1, 1 is down here. So subtracting, it's literally going to move it up instead of down. So this is totally right. You have to think backwards. This is not the way you're thinking. You're normally thinking what? You're thinking in your Cartesian coordinates, right? You're thinking, oh, well, positive's always going to go up, right? Not in this case, because 0, 0 is at the top here in the corner, and 1, 1's here at the bottom. So by subtracting, we move up, and by adding, we move down. By adding, we move over, and by subtracting, we move this way. So does that make sense? Because remember, 0's on this side, right? So if we subtract, we move this way. If we add, we move that way. So our Cartesian coordinates are the same as what we have for our UV coordinates. They lay out the same for horizontal. They lay out totally opposite of each other, inverse of each other vertically, because again, 0 is at the top and then 1 here's at the bottom. So if you think of this as fourth quadrant of your Cartesian coordinate system, over here the bottom coordinate quadrant, that's what this would be as far as the UVs are laid out, as far as that goes, in the 0 to 1 relationship. So that means that if we say the UVs here subtract step vertical, that's going to do what? Remember, 0's up here, so if you subtract from it, it's going to move us upward. So we move up, right? Subtract step horizontal is going to be, wait, what? 0, 0. So check it out. Color 0, 0 here. Pixel minus step horizontal. Okay, cool. Now we need to compute the one. Now we've already done what? A vertical step. So we're up here the whole time, all right, for all these computations. And then for what? Weight, color, 01. Yeah, so 01 here, we're setting the pixel to it. Awesome. For weight 02 here, now I'm saying weight here, but honestly these are just colors that we're pulling the actual pixels. So we're grabbing the pixels right now for the sampling. So we're grabbing the pixels from the sampling from the actual 3D card, from the texture sampling from the texture space memory on the 3D card, and we're accessing these different points in memory. Okay, and that's how we're doing that right now. We're actually moving ourselves through the memory accessory function capability there within inside this shader called sampler, a texture sampler. All right, so here we're going to move over to the right, and this is going to be our pixel step horizontal. So yes, we're going to move over 1. So that adding that one amount of space we move over, and I say step horizontal because it could be maybe we skip a pixel or something like that. Sometimes we do that, and we get better blurring effects or such. So I've seen other techniques where they well, screen space ambient occlusion is a good example of this, where they want to skip a pixel and then thus blurs across it, and you get a better result because you get a better softening of the pixels than doing the one very next right next to it. So interesting, very interesting, and then in doing so you end up getting a smoother result, believe it or not. I know that sounds crazy, but usually the reason they have for that is because saying that, so you can actually swap this up and change things around a bit on this. The reason why they were saying that is because you got to realize the pixels right next to the one you're sampling are typically very close to the one you're sampling. So if you're wanting to get a lot more blurring or a lot more variation, reduction of variation, then you're going to do a larger step size to the left or right. So that's why I'm saying that's what the step horizontal is, not necessarily just 1 to the right, but in our case, in this example, it is 1 to the right or 1 to the left, so on and so forth. In this case, we have pixel step horizontal. It's going to go to our right. All right. And then we have our, now we're going to do our vertical placement again here. So for pixels, UV. So where does that place us back at? Our pixel, our original pixel here. Okay, so it places us along this row here. So we're going to step horizontal to what? The left, because we subtracted from it. Okay, cool. So it gives us our pixel to the left, and then we're going to say pixel here. It's going to give us our actual pixel, and that's going to go into color 11. So check it out. Matches with 11 position, with 10 position, so on and so forth. All right, and in position number 12, how do we get there? Well, that's simple. We just add a step over from that pixel there. Okay, cool. And then we need to do what? We need to move down here and compute these. So again, remember, this is 0 to 1 type relationship. So 0, 0 is here, 1, 1 is here. So we have to add to move down. So that's what we're going to do. We're going to add to move down. So UV step vertical here. We're going to move down like that. And then we're going to subtract our pixel from our step horizontal to move us over here to the left. So here in this way, we get over to our left, and we sample this pixel here. Pixel here is just going to move us right here, and we're going to sample it because remember, we are already moved down for this whole row of pixels here from previously, okay, on our UVs. So we're going to sample this pixel now here. And then if we add one step horizontal over to the right here by adding it, it's going to move us to 2, 2. So that gives us color 2, 2. Now, cool, check it out. Our weights are going to correspond with our pixels. Imagine that for the colors. And then thus, when we sit there and take our color here, 0, 0, we multiply it times what we decide we want to be the weight for the 0, 0 pixel for how important we feel it is, it's going to determine the final value of this color. So how much contribution does it do when we add them all together? It's essentially the case. And so all our different weights determine how much of contribution these different colors that we sampled from the surrounding pixels around our core main pixel here. And thus doing so, we end up with our final computed color here at the very end, because we just add these up as we go all the way down. And this is with them all combined. So then we have to say the total number of elements. In this case, it's 9, because we have 9 pixels that are sampled, right? 3 by 3, so this would be 9. If this was a 4 by 4, it'd be what? 16. 5 by 5, 25. 6 by 6, 36, so on and so forth. In this case, it's a 3 by 3, so it's going to be 9 elements in here. And we're going to divide it by 9, so that way we get our final color for our pixel, our final pixel, the result there. And we say equals final pixel, and then that gives us our final pixel. And in doing so, you would get something like a box method like this right here, which is a glow shader as a good example of it, okay? So that's a good example of a glow shader right there. And that is essentially how it works. And that is how you can do box method algorithm. This is a very important algorithm. It is something we will use quite a bit, and it's something you absolutely need to know how to do for many techniques and many methods. And this is essentially how it works, and this is the mechanics behind it. So when you see them talking about these glows or blur, and a lot of times they won't even tell you the daggone code or anything of the sort, or how they're breaking it down or where this came from or whatever. This is where it came from. It's this filtering techniques. This is what happened. And they've been around for a long time on the CPU side, but they're kind of slow when you're computing it on the CPU, and thus moving it over to the GPU has caused a major increase in speed for calculations. So we're talking it's way, way faster. The GPU is really well designed for handling textures and images and computing them super fast. So they've designed the actual hardware to handle it and do that precisely. So this kind of techniques really do need to be done on the GPU side, and I think you'll get a much better result in doing so. But with that, that covers this basic technique and method. And if you want more details on this, I would have to recommend a particular book that goes over this in far more detail than I ever did, and in far more depth. It doesn't break it down in an easy to understand method like this, but once you see this broken down like this from what I presented here, I think you'll find the book a lot easier to understand. But if you look at the GPU Gems book from NVIDIA, the first book there, they have a chapter in there that's really cool, and it's called High Quality Filtering. So I can't remember what chapter that is. It's chapter 24. Okay, so chapter 24 it is. So check that out in that book, and after seeing this, it should make a lot more sense as to where the code's coming from and what's happening. And that really helps break it down, because they don't really go over this at all in the book. And I want you to see this and understand this so you understand what's happening here in our code later on and everything. And if you want to see more details on this, a lot of different types of techniques and things like that, go check it out in the book. I might go over Gauss, Lanczos, and Mitchell later on. But please check out that chapter. It is more techy, but it is a very nice presentation of filtering techniques. And I think it's definitely a worthwhile view. I definitely love bringing out other people's training materials that are excellent out in the field, and whenever it's useful. Unfortunately, most of them don't show an actual implementation of how to actually pull off something from start to finish. They assume you already know a bunch of stuff. So the point of my training series, for the most part, is to show you how to actually put something together and actually make it work. From start to finish, and then when you look at these other training materials and stuff like that, they'll just make sense to you because you've already been working with this stuff previously, and it won't be suddenly I have no idea how to do this, how to go about it. So now with this training series, with you going through it, you will have a good understanding of it, and then when you look at other training resources, you can actually make sense of them. So that was the whole point of it. Came out of a matter of a necessity and need that I've had with my students, and it's just been an issue with a lot of the training materials don't actually cover how to actually pull something off. So with that, my name is Nate Nestler, and that covers these texturing filtering techniques, high quality filtering. Well, this isn't real high quality filtering with box method, but you get the idea. It is a filtering technique, and it's not bad. It's not bad. A 3x3 gives you good results. But anyways, it is faster to do a 3x3 box, by the way, than it is to do a Gauss, Mitchell, or Lanczos. So it is faster. It's not as pretty, but it is faster. So we're going to go with the one that's faster for now. And simpler too, which is great at first here. We might get into the more difficult stuff later on that. But anyhow, my name is Nate Nestler, and this is for Hyperactive Studios. Thank you very much.